Section 13.3, Partial Derivatives. We will find and use partial derivatives of a function of 2, 3, or more variables, and then we'll also find higher order partial derivatives of a function of 2 or 3 variables. So, by considering independent variables one at a time, we can find how a function varies along a path. We do that by keeping all but that one variable constant. And this is why we say partial derivatives, because we focus on one of the independent variables. A partial derivative is the procedure of finding the rate of change of a function with one of the independent variables. The first partial derivatives of a function are the derivatives in terms of x, in terms of y, and maybe if there's more in terms of z, etc. If it's a function of two variables exactly here, then the first partial derivatives are fx and fy, which you can write in many different ways. This is the same as fx, this is also the same as fx, whereas this is fy. So the definition will be reminiscent of what we've seen in earlier calculus classes, and you can see that we are studying with a y constant, so we are reaching out when we do this rise over run along the x-axis. So we will find the slope parallel to the x-axis, and for this we will find slopes parallel to the y-axis. So, as said earlier, when we do that, we are setting all other variables constant, and we only focus on the variable of differentiation. So if we take the derivative of f in terms of x, here we would look at each term of f of x and focus on the x. Y would be considered a constant. So the derivative of 3x is 3, the derivative of x squared times y squared is 2x, y squared, and finally the derivative of 2x cubed is 6x squared, and the y remains, just like the 2 remained. If we're looking at that partial derivative at the point 2, 1, we can now substitute x equals 2, y equals 1, and after calculating we get 23, which means that if you are standing at point 2, 1 on this surface and you look in the positive x direction, the slope is 23. We can do the same with the first partial derivative in terms of y, and this time 3x is a constant, so its derivative in terms of y is 0, minus x squared times 2y plus 2x cubed times 1. So here it is, and then we plug in and we find that if we look from point 2, 1 in the positive y direction, the slope is negative 8. So this is a general sketch. It doesn't represent this particular surface, but you have a point right here, and so you can see that if you just fix y is a constant, you actually have a curve. And what is the slope of this curve, or what is the slope of the tangent line at this point parallel to the x-axis, or parallel to the xz plane, to be more precise? That slope would be, in our example, 23. Here it seems like it's rather going down. And similarly, if you fix the x value, then you are actually looking at this red curve here, and you can find the slope of the tangent line to that curve. And in this example, it's negative 8. So we are going to do that for another example. We are given the surface f of xy equals x times e to the x squared y, and we wonder about the slope in each of these two directions. So this is the derivative in terms of x. Let's check. It's a product rule, so we have to do u prime, which is 1 times v, plus u times v prime. So 1 times v plus u, which is x, times v prime. So the derivative of e to the x squared y is going to be e to the x squared y times 2xy. And this is why you have this 2x squared y, because 1 came from earlier. Similarly, if you do u prime v plus uv prime, but in terms of y, Well, you don't need to do that, in fact, because this is only, x is a constant, so you can just treat this entire thing as an exponential function with a chain rule. So it's x times e to the x squared y times the inside derivative, which is x squared. The area of a parallelogram with adjacent sides A and B and included angle theta is given by the formula A equals AB sine theta. Find the rate of change of A with respect to each of the variables. So, partial A, we take the derivative in terms of A, we get B sine theta. Partial B equals A sine theta. And finally, partial theta is AB cosine theta. Find the rate of A with respect to A for these given values here. So partial A is written here. We calculated it a minute ago, and now we just need to simplify. B equals 5 and theta equals pi over 6, and we get 5 over 2. What does this 5 over 2 mean? Well, partial A, we are observing how much the area is growing when the length of the side A is growing. So if we increase A by a certain amount here, how much did the parallelogram's area grow by? This is what these derivatives mean. So if the length of A increases by 1, the area will increase by 2.5. Notice then in this particular example, partial A is independent of A. It doesn't matter the value of A. But that's not always going to be the case. For example, if you imagine a sector like this, then the value of A would really matter. The further you would be along the sector, adding 1 unit to length A would change how much the area A increases. Whereas in a parallelogram, it doesn't matter. If I just add 1 unit of A, the area will increase by the same amount always. Higher order derivatives, or higher order partial derivatives, to be more precise, is the process of taking the second and third, etc. derivatives. Just like in regular calculus, we have to be more aware of the writing here. This is partial squared, partial x, partial y of f of xy, or more conveniently, fxx. So in the example here, we are looking for all second partial derivatives of function f. We are going to calculate the first partial derivative, fx, and we get 5x to the 4 minus 8xy. We can, since we are here, we might as well calculate the other first partial derivative, so fy equals negative 4x squared plus ey. So there's 4 second partial derivatives. We'll see in a minute that really there's just 3. But to find fxx, I'm going to have to take the derivative of this in terms of x again, so it becomes 20x cubed minus 8y. And if I want to find fxy, this should be an x, I'm going to take the derivative of this in terms of y, which is negative 8x. Fyy requires me to take this first partial derivative and differentiate it again in terms of y, and I get e to the y right here. Fyx requires me to take this and take the derivative in terms of x, so the answer is negative 8x. And we notice that fxy equals fyx. We won't prove that, but it is always true. And in fact, it's the same for third partial derivatives. No matter what the order of differentiation is, if you proceed through derivatives of the same variables, you will always get the same answer, which can be useful sometimes strategically to differentiate in terms of one of the variables first, because you can see the derivative will simplify significantly. So, Find the third partial derivative, fxyy. So we could do fyyx or fyxy. We would get the same answer. And if it was more convenient, we might want to do that. Here, it doesn't appear that there's any value in switching the order of differentiation. So let's start with the first partial derivative of f in terms of x. It is going to be e to the y plus 2xy squared. And then we differentiate this in terms of y, so it's e to the y plus 4xy, and then we differentiate it in terms of y again, and we get e to the y plus 4x. So the theorem here is what we just talked about. Partial derivative differentiation doesn't matter what order you do it in, it will always be the same. So fzyy is the same as fyzy, and so on. So that's it for section 13.3. Thank you for listening.